And before I launch into the talk, I want to just draw attention to a couple of resources for folks working on hardware. The first of which is a factory tours group that I run out in the Bay Area. And it's an opportunity for folks that are working on hardware, whether they're starting a product or work at a product development company, to go and see product actually get made. I think the benefit is that you look on Kickstarter, for example, a lot of people will design these things not without a deep understanding of manufacturing, and it puts them sort of at risk of that thing not turning out as well as they like. So if anybody's out in the Bay Area, I'd love to have you join me for that. But if somebody's out here and sort of interested in starting a New York sister group, come track me down. The second thing that I wanted to highlight was hardware office hours. And what we're trying to do is connect folks that are sort of starting hardware projects with industry veterans that really know about manufacturing or distribution or some other area as a way to really educate some younger folks on the process. So if you want to be connected up with somebody, or if you're in a situation where you have some experience to share, that's something else that I'd love to have your help with. And the final thing is is hardware stack exchange. So I think it's been neat to see with software how if anybody's developed software, oftentimes if you run into a puzzle, if you Google it, the first thing that comes up is stack exchange with somebody who's had the same problem, and then somebody's answered nicely with a solution. So I think for people that are starting hardware, it'd be wonderful to have a similar resource. So if you have questions or if you think you can provide answers, I'd love to see folks on that. Okay, so I'll get started then. So what I want to talk about is two styles of electronics manufacturing. One involves surface mount components like these ones, and I'll pass these around in a moment. The other is through-hole. And I guess the way that I'm going to sort of work through their differences is with my experience sort of as a maker working on a variety of different projects. So for me, my time really began in 3 years ago at the 2010 New York Maker Faire. And there, it was striking to see that it seems like there's two technologies that were really exciting and really democratizing for folks wanting to get into this. One was MakerBot released their Cupcake, and the second one was Arduino was sort of highlighting their Uno among some other boards. And I think that for me, at my day job, I worked on the controls of a conveyor, and so I thought it'd be fun to go and give the microcontroller, the Arduino route, a go. So it started out just to sort of communicate a little bit more about what I mean when I say through-hole and its relation to Arduino. I think imagine a number of you have seen resistors that look like this, or little LEDs that you poke into boards. Those are used in complement with the Arduino. So the Arduino you can connect sensors of a variety from light, sound, whatever, and then put out motion or sound or light or whatever. So it's a great way to go and connect what you're working on to the world. So I think there are three things that make the Arduino awesome. So I think the first is great design. It's just really easy to use, and I think where that comes from is Massimo's point of view that it's really about users, not megahertz. So we really spent a lot of time designing it to make it just a joyous experience. I think the programming language for it is pretty simple. So it's something that you can go and just get started. And also, when you're changing the firmware with a lot of the old microcontrollers, you'd oftentimes be in a situation where you have to go through this tedious process, whereas they wrote this nice software. You just click a button, and then off you go. I think a second nice thing is you can prototype really quickly with the designs. Just unplug and replug the wires. I think the final thing that makes Arduino great is that you have a great community. There's lots of resources, both electrical schematics and software blocks of code that you can, if you want to do something, you can get started really quickly. So for me, my first project was a light controller. The light switch next to the door in my garage didn't work, and so I was used to stumbling and tripping over stuff on the way to go and work in my shop. And so what I did is hooked up a little infrared sensor that would detect when I walked in the door, and it'd just turn on the light. Really simple circuit, but it was just a nice way to get into Arduino. I think the second thing that I worked on was a fan controller for my computer. The fans would usually be just going full blast all the time, and it was really loud. But when I was in a situation where I wanted it to be a little bit more quiet when it wasn't super busy, I needed to sort of control how much speed the fans were and how cool it would be. So I just sort of put in a little temperature sensor, and the Arduino would go and sort of vary the fan speed in order to achieve that temperature. Then a little bit more ambitious project was an autonomous car. It was neat to see with Google and the DARPA Grand Challenge how folks had made these big cars that they were able to go and drive from point A to B without any person in it. So that was the next project that I was working on. And I think you can sort of see kind of what a mess it was in terms of having just a couple boards all over the place, wires going everywhere. And it was sort of in doing that I really came against some of the limits and sort of borders with using Arduino. And I think a couple things that I wanted to highlight. So I think the design was such that it was kind of fragile. So you take a look back at the wiring on here. Every time it crashed, the wires would just go everywhere, and it was time to go and rebuild it. The second thing is that the components are really big. I think the autonomous cars are something that they can bear a little bit of extra weight, and it's not going to have a huge strain on batteries. But as you see more of these like Internet of Things or wearables or drones, that's where every little last gram matters, and where the through hole just adds some extra weight. I think the third thing that I was bumping up against as I was working on the car was just the fact that the component section is limited. Really, since the 80s, people in industry barely use through-hole, maybe except for some connectors and some big electrolytic capacitors. And so it's frustrating. Like if I saw this cool chip that I wanted to use, it wasn't available unless SparkFun or Adafruit had a breakout board for it. I think the final thing is just the fact that it can't scale. So they have some machines, but they're just super expensive. It's hard to get your hands on them. And so for the most part, when you're doing manufacturing, it'd just be by hand. And so I think this has two consequences. I think first is that you have to do a conversion process if you want to go and make more than a couple of boards from your through-hole design to the surface mount style that I'll talk about a little bit later. So I think the frustrating thing about that is that one of the purposes of the prototype is to sort of test a bunch of your technical hypotheses. And if you go this through-hole approach, it's a situation where you have to go and so like you have a whole new set of hypotheses when you make that transition. So now I want to talk a little bit about surface mount as an alternative, and I'll just sort of pass around a board and some components that are examples of this style. So if you can just send them all around. So whereas the resistors are in the old style usually had those leads and a big bulb, these come on tape. And there's these little components that come along on the tape that get placed on the surface, and that's how they get their surface mount name of a printed circuit board. So one of the options that I looked to with that autonomous car, after being frustrated with the components and the wires going everywhere and all those other issues, was hand assembling with surface mount. So buying a microscope, getting some tweezers, and just go and, based on the design that I had in my head, pick up the little components and place them on the board. So I think there's a couple things that made this not optimal. So I think one is the frustration of just like it's hard, because the components are so small, it's hard to place them exactly where you wanted to place them. And when you're doing a design, again, it's sort of that test of, you want to be testing your design, that's what you're doing, not testing how well you can sort of hand manufacture the boards. I think to just give you a sense of the size of a lot of them, some of them are as small as like 5 human hairs by 10 human hairs, so it's just, they're not that big. And your phone is full of ones that are even smaller. So I think the final thing is just sort of a question of like, how do you want to be using your time? So like when I was working on this project, I wanted to go and like play with the design and sort of figure out how to get it working. I didn't want to spend time sort of hunched over this microscope with the tweezers just trying to bang out the boards. That just wasn't what I had in mind. So I think one of the big ideas that comes with surface mount when it's done properly is this idea of digital fabrication. And what I mean to say with this, and you can sort of understand it by analogy to software and mechanical design. So with software, it's great in the sense that you can write code, press compile, and then all of a sudden it's pushed out. You can go and debug it, you can go and show it to customers, and you can iterate really quickly. The same's true with mechanical design. I think particularly with the advent of 3D printers, you can go and design something in SolidWorks or whatever CAD software you like, send it off and get it 3D printed right back, and then you can go and see, did it fit exactly, does it feel right with customers, all those type of things. So I think there's 3 things that make digital fabrication really powerful. I think one is it's instantaneous. When you're in software, you're able to go and test a lot of things even before you even have to bring something to reality. I think the second nice thing is it's scalable, that you can go and sort of say like, hey, I want 100,000 of these things, and some factory would be able to go and sort of take your design and maybe make minimal modifications, and off they'll go, making a ton, instead of having to redesign from if you start with through-hole. And the other neat thing is portable, so you can share design. So if you're working on a design and you have a friend that wants to try something similar, you just send him the design files and he makes something that's the same instead of having him try and decipher and manufacture by hand. So what I was looking for is digital fabrication, but for electronics. So something that would allow me to design a circuit board in Eagle, Altium, whatever CAD software, and then pretty much press something that would go and give me the physical board out of it. When I looked around, the main option was going to get a contract manufacturer to go and help out with that process. So this is somebody who has a big sort of room-sized robot that they would load your design in, manufacture the board, and then send the board back to you in the mail. I think there was 3 things that really struck me as I was trying to make a board with this process. I think the first was it was glacial. Oftentimes it'd be weeks would be the cycle time. When I was used to sort of doing software, you could do it instantaneously. I think the second thing is it's cumbersome in the sense that I spent a lot of time just talking back and forth with the contract manufacturer in order to make sure that what I wanted was what got made. I think the third thing is it's expensive, and I'll talk a little bit more about what I mean when I say that. So I think I'm not the only person that sort of has sort of frustration with this transition from software and the design process in there to design process in hardware. So this is a woman who does an Internet of Things company called Pinocchio, and she was doing like UX and other design type stuff. And when she started her Internet of Things company, it was just sort of this jolt of it takes a lot longer for each iteration. So I think this is a diagram of what I mean when I say it's cumbersome. So you sort of start out with designing the board, and then you have to send some design files off to a fab house to make the PCB. You have to send some other design files off to a contract manufacturer that's going to be able to do the assembly. You have to pull out from your design the bill of materials with all the components that you want, send that to the contract manufacturer, but also sort of place an order with the distributor to make sure that they give you what you want. You have to make sure that everything gets shipped to the right place, so that when the board's done, it gets shipped to the assembler, the components shipped to the assembler, and then finally you'll get your board back. And so this is what I mean when I say it can be a big distraction, just the execution process of getting a board made by a third party. I think price is another consideration. I think it's frustrating when you're talking to a contract manufacturer and I want to do this quick cycle. I don't want to spend $1,400 every time that I do it. So I think that when I was looking at the sort of existing option of this, like for digital fabrication of these big room-sized machines, it was like sort of putting it in software terms. It's like you press compile and you have to wait a week or so to see what the result is. You have to go and spend $1,400, and you have to spend hours of your time just working out the logistics. So that didn't feel like a very attractive option either, in addition to the hand assembly. So I think I think now I will return to sort of that MakerBot idea that I saw at the New York Maker Fair in 2010, and it would been neat to see that just as software had gone from these big room-sized mainframes to these machines that could be on your desk or on your lap. Similarly, in MakerBot, I think it was inspiring to see sort of for mechanical design, you have that same type of pattern where you start with these big sort of giant refrigerator-sized printers that are just in university labs, big industrial R&D spaces, and then they go and move to something that I could use on my desk. So I decided to do something that was kind of similar with the MakerBot, but for this electronics approach. So the idea was to have this desktop robot that you'd be able to sort of design the circuit board and software, send it to the robot, and then it would manufacture the board. So the sort of central idea for the interaction of how we're hoping to use the robot is really inspired by document printing. So I think it's great when you're printing a document. Setting up the printer is just a matter of you snap in the toner, you put in the blank paper, and then you're ready to go. Similarly with electronics, to me it feels like it should be you put a bare PCB, you put in components, and you're set and ready to start. I think the software interaction should be the same. So it's a situation where you can type the document in Word, file print, and there's your document. The goal is the same thing with electronics. So instead of doing file print, it'd be file make from Eagle, Altium, whatever software it would be. So I think in order to be able to sort of really go from this idea where you start with just sort of a design and end up with a functioning board, the machine has to do a lot of things. So it needs to be able to make PCBs like that one that I was passing around. And one way to do that is the routing process, where you start with that blank board and it cuts out the copper, leaving just the little bit remaining that you want to conduct. You also have to go and put down solder paste. This process of it's a sort of glue-like conductive material that's an interface between the components and the board. Then it's pick and place. So you have the components that that you have on the reel, and you have to go and actually physically put them on the board according to the design. Final step is you put it in a reflow oven. It's an oven that's precisely temperature controlled such that the board and the components get bonded well. The final step is testing, just to make sure that when you load the board in, it turned out all right. So let's see if that. Sorry, it looks like let me get the video. Oh, there it goes. So just to give you sort of a sense of where we are right now in terms of what the interaction is for the robot, take a look at the video. So following with that printer setup analogy, so you put in a tray of a variety of different components, you put in the boards, and that's really all it is on the hardware side. From the software perspective, you design the board in Eagle or whatever you like, export the manufacturing files, then drag and drop them into our software. At that point, the robot takes over and is able to go and do a lot of the setup itself. So it's able to figure out exactly sort of where the board is by going to sort of take pictures around the whole surface of the board to figure out what its orientation is and what its position is. I think an added benefit of this type of pattern is the fact that you can put the board in any way you want. You can throw it in as like a frisbee and be able to figure out where it is and still do the placement. So the computer vision is also involved with finding the components. So you load in the components in that tray that I mentioned, and the computer vision is able to go and figure out where each of the different ones is. So this is another step where it's just one less thing that you have to deal with and tell, here's where this component is, here's where this component is. It sort of saves some of the tedium. Then sort of just press make is the goal, and off it goes picking and placing. So the way that it works is as a vacuum. And so it drives to the component, picks it up, makes sure that it is where it was supposed to be, and then drives over to the board and drops it. So after the board would be filled with components like that, the next step would be you would go and put it in that oven that I mentioned before for it to be reflowed, and then you do test to make sure that it worked out. So we have the robot at the show over here, but one of the really exciting opportunities for us to use it was at a hardware hackathon. I think in many ways, software hackathons really demonstrate the power of software and the tools associated with them right now, in the sense that you sort of you can really from over the course of a weekend, you could come in with pretty much an idea and walk out with a decent application. And it's because all the things that exist in software that's really possible. And so I think it'd been frustrating going to a bunch of hardware hackathons and so we do all this design and it's like, here's the schematic or here's the board layout is what we have at the end of it instead of here's the PCB. So we went to this hardware hackathon and helped teams to go and actually build out the boards that they had designed. And it was as just sort of a demonstration of what was possible. So I think in many ways our goal with this machine is really to go and do anything that is going to be electronics. So I think from like the wearables, the Internet of Things devices, all the way to the drones and other autonomous vehicles. So I think that just to sort of sum up, it seems like it's a situation where I sort of started out trying to understand what's going to be a good way to build this autonomous car, and the through-hole approach just was not a very attractive one. And so I switched over to surface mount, and the nice thing about that was you're able to use that digital manufacturing approach that allows you to go and sort of quickly iterate through your designs. So the final things are just some ways that you can go and help if you want to be involved with a project. So I think one is being sort of an early adopter. I think that it's a kind of a new technology, and we really welcome feedback and guidance on the design. I think the other thing that we're really would love to give you sort of as a way to say thanks for that help is a discount on the price. So we're also, after we lock down the design a little bit more, we're planning to do crowdfunding, and so that's something that on the horizon coming up shortly. There's also two folks that we're hoping to have join our team. One to help run our crowdfunding campaign, and the other one doing manufacturing engineering. So if you or somebody you know is in one of those categories, please come track me down. I guess the final thing that would be wonderful is if you guys know somebody at Eagle or DipTrace or one of the Altium, anything like that. In order to really achieve that file make, you need to have integration with that software. And so if you know somebody that's in that group, that would be really big help. So that's what I have. Thanks so much for your time. Okay, so I guess it sounds like 3 or 4 minutes of questions is if anybody has anything they want to ask. Oh, I guess one final thing is we're just right over there, maybe like 30, 40 feet over there. So if you want to see the robot in the flesh, please come stop by. Is there a microphone or something like that? I can't hear it all. I can't hear it. So the question was, what are the differences when you translate from one design to another? So like from a through-hole design to a surface mount one? So I think there's a couple of them. So I think one is that you have to you just select completely new components. So instead of having sort of through-hole components with electrical characteristics that they have, you have to go and transition to something else that's going to be surface mount. I think the second is also just laying out the board. Instead of having the breadboard where you poke in all the design that you want, you actually have the traces, and that's going to connect the different components. So that's just design time that you need to go and instead of having the through-hole just wires, you transition to actually traces. Any other questions? Yeah. Okay.
You only showed a tray with one set of components. Do you have to go in and swap trays for each type of component?
So it's a really good question. The question was, do you need different? Do you have only one tray per type of components? And I think our goal is to try and make it kind of like that, continue the document printing analogy with toner, how you put in a couple of different toner styles and you're able to go and make a huge variety of different colors. So our goal is to have a couple of different trays that you would go and load in the machine. So each tray would have a diversity of components. So maybe one would have a bunch of resistors and capacitors, another one would go have microcontrollers and crystals and things like that, and you'd just be able to switch those out. Exactly right. So the second question was about pricing, and what we're planning on is $5,000 for the pick and place, and then $1,000 for each other capability. So $1,000 to do solder paste, $1,000 to do routing, and so on. Yes. So the question was about what component sizes can the robot support, and. So the question was, can the robot distinguish between different component sizes? And it can, and the way it does is you have templates, so for each of the different styles of component, and then the computer vision will compare what it sees against that template. Your time? So the question is, can the robot tell apart different parts that are the same package? And I think that that's something that we're working on, but for the first version, the plan is that the tray would have some indication to say, here's what's in the tray, and then based on that information, be able to go and populate the board. But you can change out stuff into the tray. All right, thanks so much for your time.